Have you ever just looked up at the night sky, seen one of those tiny little lights moving, and thought, what is that? Well, those are satellites. There are thousands of them circling our planet right now. But that brings up a pretty big question. How in the world do they stay up there? That's exactly what we're going to figure out in this explainer. I mean, really think about it. Why don't they just fall down? There's nothing holding them up, right? So what's stopping these thousands of incredibly expensive pieces of technology from just crashing back down to Earth? It really does feel like it defies the laws of physics.
Well, here's the secret, and it's gonna sound a little strange, but they are constantly falling. Yeah, you heard me right. The entire trick to staying in space isn't about escaping Earth's gravity. It's about using it in a really, really clever way.
All right, so let's get into this whole never-ending fall thing. To really wrap your head around it, you have to picture an orbit as this perfect, high-speed balancing act. So what exactly is being balanced? Well, on one side, you've got the satellite's incredible forward speed, its velocity. That's the powerful push it got from its launch rocket, and it wants to travel in a straight line forever. But on the other side, you have the constant, relentless pull of Earth's gravity, which is always trying to pull it straight down. An orbit, well, an orbit is just the beautiful, continuous dance between those two powerful forces.
Now, to really visualize this, we can turn to one of the most brilliant thought experiments in the history of physics, Isaac Newton's Cannonball. It's a fantastic way to understand this.
So Newton imagined putting a cannon on top of a crazy tall mountain. Now, if you fire it with just a little bit of power, the cannonball flies for a bit, arcs down, and boom, hits the ground. Okay, simple enough. Add more power and it flies farther before it hits the ground. But, and this is the genius part, what if you could fire it fast enough? We're talking something like 30,000 kilometers per hour. At that insane speed, the cannonball is still falling towards the Earth, but the Earth's surface is curving away from it at the exact same rate. It's literally falling, but constantly missing the ground, and that right there is an orbit.
You know, this constant fall actually creates an elliptical path, not a perfect circle, and this path has two really important points. The highest point, where the satellite is farthest from Earth, is called the Apoapsis. The lowest point, when it swings in closest, is the Periapsis. The satellite actually speeds up as it gets closer to Earth at Periapsis and slows down at Apoapsis. And by firing little thrusters at just the right moment at these key points, engineers can tweak and adjust an orbit's shape and size with amazing precision.
And this brings us to what might be the most important takeaway here. A satellite in orbit has not escaped Earth's gravity at all, not even close. As NASA puts it, gravity is actually what's providing the centripetal acceleration needed to keep it in orbit. It's the force that's constantly yanking the satellite inward, bending its straight path into a curve. See, without gravity, the satellite would just zip off into deep space in a straight line. Gravity isn't the enemy of an orbit, it's the essential ingredient that makes the whole thing possible. Okay, so now we know how satellites stay in orbit. But where they orbit is just as critical. And generally speaking, Earth orbits fall into two main categories, high orbit and low orbit. And believe me, they each have very different jobs. And the difference in altitude between them is just staggering. Low Earth orbit, or LEO, is pretty close to home, cosmically speaking. It's anywhere from about 160 up to 2,000 kilometers away. But geostationary orbit, or GEO, well, that's in a whole different ballpark. We're talking a whopping 35,786 kilometers away. Now, there's a very special reason for that very specific number. At that exact altitude, a satellite's speed makes it take exactly 24 hours to circle the Earth, the same time it takes our planet to rotate. So from our point of view down here, it looks like it's just hovering in one fixed spot in the sky. And that is incredibly useful for things like satellite TV.
So why would you pick one over the other? Well, it's because choosing an orbit isn't just about how high you go. It's about a whole series of really important trade-offs, mainly between communication speed and how much of the Earth the satellite can actually see.
Let's break down these differences. LEO satellites are close, so their signal is really strong, and the time delay for a signal to go up and back, what we call latency, is super low. The downside? Their view of Earth is pretty small, so you need a whole bunch of them, a whole constellation, to cover the whole planet. GEO satellites, on the other hand, have a gigantic view. Just 3 of them can see almost the entire globe. But because they're so far away, their signal is weaker, and there's a noticeable time lag. The key thing to remember is that there's no single best orbit. It's all about picking the right tool for the right job.
And hey, don't just take my word for it. This isn't just Siri. Researchers at the University of Limerick put this to the test, and what they found was that using a LEO satellite didn't just cut down the delay, it made download speeds almost 14 times faster than a GeoLink. That is an absolute game changer.
This chart right here really drives that point home. Look at the difference in latency. A signal to a geosatellite and back took 627 milliseconds. That's over half a second. For the LEO satellite, just 91 milliseconds. Now, that might not sound like a lot, but for anything that needs to happen in real time, like a video call, online gaming, or say remotely controlling a robot, that difference is absolutely everything.
So, we've seen the physics, we've looked at the data. Now let's see how this all works in a super high-stakes, real-world scenario, piloting a robot at the bottom of the ocean from hundreds of miles away.
For this experiment, researchers headed out to sea, off the coast of Ireland. Their mission was pretty wild: to control a submerged robot, an ROV, from a control station back on dry land using only a satellite connection to do it.
And they tested two completely different systems. On one side, you have their LEO network setup, connecting through a Starlink dish. On the other side, the GEO network, using the ship's more traditional satellite system. The goal was to see which one performed better in a situation where every millisecond counts.
And the results were pretty amazing. I mean, first off, both systems actually worked. They could successfully pilot the robot with either one. But the LEO connection, with that super low latency, made the controls feel instant, totally responsive. And the data speeds? It wasn't even a contest. 51 megabits per second download on LEO compared to just 3.7 on GEO. This test proved that LEO isn't just viable, it's ideal for really complex remote work, like a scientist sitting on shore using a robotic arm to collect a very specific deep-sea sample.
Okay, so after all that physics and a deep-sea robot adventure, what are the big things to remember from all this? First and foremost, remember that an orbit is basically a fall that you never land. It's not about escaping gravity at all. It's about that perfect, delicate balance between moving forward really, really fast and being pulled down by the Earth. And second, where we choose to put that orbit, way up high or down low, is one of the most important trade-offs in modern technology. That single decision fundamentally shapes how we communicate, how we explore our planet, and how we see our world. And that leaves us with one final big question. As we continue launching thousands upon thousands of new satellites, building these enormous mega constellations in the sky, what will the future of our connected planet really be built on? Will we choose the incredible speed of low orbit or the rock-solid wide coverage stability of high orbit? The answer to that is going to define the next generation of how we all connect.